just by construction, because no action token in the chain of thought has any direct effect on the reward, kind of by construction. I'm ignoring some of the process reward models if you're familiar with that. And 3, no good value function estimates are available. And this is kind of one of the initial like eureka moments of LLM reinforcement learning recently, is that PPO with a learn value function has been largely replaced with GRPO, which uses a group relative advantage function. So okay, given these given this insight, there's also a couple other reasons why we would want to use ES. So the first one is that ES is a black box optimizer. So it optimizes systems, not policies. This is a critical distinction to make, because that means that you can handle complex samplers, multi-agent systems, diffusion models, and a bunch of other systems that people currently use at deployment time. It would be very hard to turn this into an actual formal policy and find out, oh, what's the probability of generating this exact sequence of actions. A second point is that OpenAI's ES paper found a linear speedup with batch size to reach convergence. So this might be more impactful for the HPC community, because typically in backprop-based learning, you'd want to have like a single GPU for as long of a time as possible, so that you can take as many updates as possible, versus like 1,000 GPUs for 1 hour, right? So you'd rather have 1 GPU for 1,000 hours than 1,000 GPUs for 1 hour, because you can take more steps. But interestingly, in evolution strategies, and something that we've confirmed in our paper, is that yeah, you can. It actually doesn't matter. Like compute is compute, and you can actually parallelize it almost linearly to reach convergence, which is a quite beneficial property when you have these gigantic data centers with like hundreds of thousands of GPUs. Yeah, and then so like in particular, other deep reinforcement learning methods typically do not benefit from much larger batch sizes. One reason for this is like from the math area, ES optimizes a smooth and loss function. So it can take larger steps at a bigger batch size. And the final point is that you can handle non-differentiable components, so you can do neurosymbolic AI for the first time. You can actually train the neural network components with awareness of the symbolic components. Yeah, because you don't need to back off to the symbolic things. Okay, but then even though we had all these reasons why evolution strategies might make sense, it's still like quite absurd, right? Because evolution, the way it works is you add noise to the parameters, right? So you need a different copy of the model for each variant of the population. So if you have an 80 gigabyte GPU, which is like a pretty large H100, you could only have a batch size of 5 if you have a 7 billion parameter model with bfloat 16. And even if we could have a larger batch size per GPU, this still would be very slow, because we aren't reusing matrices for the entire batch. So like you lose a lot of the benefits that you get from GPUs. The second point, which is something that we just need to verify empirically, is that there's just this gut sense that we're throwing away a lot of information about the actual actions generated by the policy. So maybe like a hunch we could get is that we might need a much larger batch size compared to a comparable policy gradient method. It turns out from our results that this actually isn't true. It just feels that way because like, oh, you're just doing random noise and you're getting some signal out, but actually you get quite a lot of information, so you don't actually need a much larger batch size. And then the third part is that we're assuming that LLM parameters are robust enough to remain salient despite adding noise. So like you're adding noise to the parameters, right? What if that just completely breaks the model and nothing works anymore? So that's one concern. But then the opposite concern is like, okay, is it still sensitive enough to have a difference in performance? So that's something that we just didn't know coming into this project. But I don't know, I guess we just took a leap of faith and tried to see what happened moving forward. Cool. So a bit of background. You don't need to understand this equation. I guess if you want to understand something, it's the reinforced learning algorithm, which is at the bottom. I'm just putting this up to show like how kind of complicated this is relative to what evolution strategies does. Yeah, you're basically, if you know how good a trajectory is, or like specifically an action is, this is what the advantage function tells you. So we won't dive too deep into this because it's not super relevant. But basically, you can think of this as like doing supervised learning, but you're weighting it by how good the on-policy rollout generated was. And then what GRPO does is it also does important sampling so that you can take multiple update steps instead of just doing one. Okay. The second, so this one is the more critical point to understand, which is how OpenAI's ES method works, which is a simplification of prior ES works. And if you look at natural evolution strategies, Schmidt-Huber has a great paper on it, and I have to mention him, otherwise he's he's going to come after me. So the way it works is you have theta, which is like kind of the mean parameters of the model. You sample Gaussian noise with some pre-specified hyperparameter sigma, which is kind of a scale factor. And it turns out that the gradient with respect to kind of this the smoothened fitness function is equal to 1 over sigma times basically the fitness weighted average of the noise. So then the way that you do this is you just update this with SGD. So you just take a bunch of different random noise samples. You estimate what the fitness is for those. And the fitness could be quite noisy. It could be basically anything because you don't need to backprop to it. You just take fitness times noise, and you just take the average of that. Cool. So that's pretty much it in terms of how evolution strategies typically works. And there's also a bunch of existing tricks. So the first part, which is quite important, is anesthetic sampling. Basically, when you're sampling the noise, you actually want to sample pairs of noise in opposite directions. This is just a way of doing variance reduction. Because suppose all scores are around like 100. So maybe in this direction it's going to be 101. In this direction it's 99. If you didn't do this anesthetic sampling and you just sample a bunch of different directions, you get very high variance in your gradient estimate. But this kind of implicitly does a baselining for you. So this is a very handy trick. People also do rank transforms. So instead of taking the actual fitness, they rank the different population members and use that to determine what the update is. And then also people use better optimizers and standard neural network tricks because you're basically getting a pseudo gradient without needing to do backprop. Okay, cool. So now that I've explained what ES is and kind of its simplicity from a kind of mathematical perspective, the key thing that I felt was missing with evolution strategies or classic evolution strategies was the hardware awareness. So maybe this is going to be more familiar to the HPC community. So in particular, I was thinking about the issue of arithmetic intensity. So hopefully just review for most of us. Arithmetic intensity is calculated as the number of operations divided by the total number of bytes written or read. So on each 100 GPUs, you approximately have like a petaflop if you exclude sparsity. It's a bit hand-wavy of a number because it depends on the exact configuration of what the matrix size is, but it's at least a good ballpark for us to get like some numbers in the picture. So they have a petaflop and 3.35 terabytes per second of GPU memory bandwidth. So reflying threshold is approximately 300 ops per byte. So this is just like a number to keep in mind as we're moving forward. So as a warm-up, let's try to do batch inference for like large neural networks. So imagine you have a batch of inputs, B by dn, and a weight matrix that's D out by dn, and you have S bytes of precision. So in terms of the memory that you need, the input is going to be B by dn times S, D out times dn times S, and output is like the output matrix, B times D out times S. And the total number of operations is 2 D, B, dn, D out. Just go through the thing in your head. And multiplication and addition are both treated. So when S equals 2 and D out and dn equals M, just to like simplify it down so we can get some clean expression, arithmetic intensity essentially simplifies down to B times M divided by 2B plus M. So the key idea here is that like there's a multiplication at the top and an addition at the bottom. So if you have a sufficiently large model, there's going to be some batch size at which you hit the arithmetic intensity desired. So to get 300 ops per byte with M equals 8192, so this is like a decently large model, or at least like a 14 billion parameter model, which is like kind of the largest models we used in the public version of the paper. This requires a minimum batch size of 324. So this is reachable. So now let's look at evolution strategies. So remember what I said about evolution strategies, you have a different variant of the model parameters for each population member. So if each population member needs to do one rollout each time, right? So you basically have a batch size. The batch size is equal to the population size in this context. So the key difference here is that the weight matrix is different for each member of the population. So it's B times D out times dn times S. So notice the multiplication here. The number of operations stays the same critically. So this is already like quite efficient in terms of operations, but memory increases. So the arithmetic intensity is basically the B's cancel out. So when S equals 2, D out times dn equals m. Arithmetic intensity simplifies to m divided by 2 plus m. So notice that it's insensitive to the actual batch size. It's kind of treating this as batch size 1. So it's always less than 1 and 1 factorial. So this is kind of the critical issue with evolution strategies. So the key idea of egg roll is how can we structure the perturbation so we reduce the amount of memory we actually need to move. So I was thinking, okay, instead of sampling the full d out times d in matrix, what if we just keep track of a low rank structure? So we have AI times bi transposed kind of low rank matrices. In practice, we use r equals 1, so it's even better because you basically just have 2 vectors and you do an outer product. So what our theory shows, and this was like a lot of theory, but I'm not going to get into for this talk, is that in the limit as r increases or parameter dimensionality increases, we recover the same update as evolution strategies. And this is kind of the main theoretical motivation behind EGRO, evolution guided general optimization by low rank learning. Cool. So a key, like, I guess, implementation detail is that if you just expand out this low rank structure back into the full rank matrix or into the full matrix, then you've just lost all of your arithmetic intensity benefits because you just created this full matrix again. But instead, we can just break it down into matrix multiplication plus cheap work. So if you have, so basically you keep the same benefits of batch inference plus a lot of cheap but inefficient work. So because it's even though it's inefficient, it's cheap, so it kind of doesn't matter. And if we go into the arithmetic intensity, a lot of text on the screen, but the key point here is that even though it's a much more complicated expression, the b's don't cancel out fully. So if you want to have, like, kind of keeping the same assumptions as before, if you want to have the desired arithmetic intensity, you need a minimum batch size of 352 compared to 324. So basically, you're able to achieve this roofline threshold that you want. Okay, now there's a question of, okay, you're doing this additional cheap work. How much arithmetic overhead do you need? So there's an additional b times m times 4r plus 1 flops. So it's an additional compute rate of this. So it's basically negligible. Is the long term of it. It's like 5 over like 100,000 or like 10,000 or something. So this is basically negligible. So in practice, what we see is that relative to PPO and additional and existing policy gradient methods, we're almost like 2 to 3 times faster. The bigger bar is saying if you pre-generate the low rank perturbations, and the shaded bar and like the darker bar is if you have to regenerate it from scratch using PR and G keys. But in either case, it's still like much better than any existing method. And you might see the OpenES at the bottom down here, which is like, so we're basically 100 to 200 times faster. Yeah, and there's some details at the bottom. Cool. So yeah, this is kind of the high-level diagram of like how this works in a mathematical sense. So you have these low rank perturbations that you're adding to the fitnesses. You still take the fitness weighted average, and you get the rank and update. Cool. So there's a bunch of results. We started with tabula rasa reinforcement learning, inspired by OpenES work, and we see that yeah, we're basically on par or better than OpenES. This is a bit of a strange result because all of our theory was saying, okay, what if ES was like the thing that we want? And we're just doing like a crude approximation to this. But we actually see that for some reason, this is better. And we do like fair hyperparameter sweeps for all of them. Like basically everything is tuned from scratch. I guess like technically OpenES has a bit of an advantage in our hyperparameter scheme because it doesn't have the rank hyperparameter. But even with that, we see it's slightly better. So there might be something to say about like a low rank exploration actually helping us more than we expected. Okay, and then afterwards we tried this for reasoning experiments. So we started with countdown, which is like a decently hard problem that RL kind of struggles at because it's more of a logic-based problem that isn't really put into the training data of LLMs currently. And what we see is AGRO just like smoothly increases. And GRPO, sometimes it gets lucky, but oftentimes it's worse. So yeah, we're just better. And all the x-axis is wall clock time. You see, we use the same number of GPUs, basically same everything, but we tune the hyperparameters differently so that each one is like as fair as possible. Because what we see is that AGRO benefits from a much larger batch size, whereas GRPO, it prefers more frequent updates. So even after tuning all of those and being as fair as possible, these are the results we get. We also tried this on GSM-8K, which is a math reasoning benchmark. It's like grade school math problems, 8,000 of them. And yeah, for the 7 billion parameter language model, RWKV, we still see the same, like a similar benefit. And yeah, we also did like a more exhaustive math reasoning benchmark, and we see, yeah, we're still on par, if not better, than GRPO. It's a little bit insensitive to these because there's a small number of questions. And then for RWKV 17 G14B, this is something that we weren't able to train with GRPO on our systems because just adding Atom and all of the additional memory overhead is basically impractical, and it didn't really change from the baseline results. Whereas Eggroll, it just increases significantly. Cool. And then kind of just to show off how strong Eggroll could be, we also created a novel architecture for pre-training, for language model pre-training. We call it the evolution evolved generative GRU model. And yeah, we basically take an existing like transformer-based language model and we try to undo all the things that we thought was absolutely necessary. So no transformers, we use a nonlinear RNN, which would basically be like previously impractical to try to train end-to-end because backpropagation through time is extremely expensive. But with ES, we don't care, right? With what we're trying to emphasize is with evolution strategies, we want to have AI algorithms that are best for inference time, not have to compromise because we have a separate training phase. Cool. So then we compared our egg model trained with Eggroll against a standard transformer with backprop. Both of them are using the SGG optimizer. And what we see is that with sufficient compute, we actually beat backprop, which was quite surprising for us because we would have kind of expected, like coming into this, that you would actually approach it in the limit because you're going to get to the gradient like in the limit as population size goes to infinity. But actually, we believe it's because of the smoothened loss function that we're using in evolution strategies and Eggroll specifically that allows you to actually squeeze out more performance out of the data that you currently have. And this is all using the same amount of data for each training step. So we're basically saying as population size increases, but we have the same amount of data, so we're just pumping in more compute. How does performance improve? I guess one caveat is that we require 180 times more compute or 150 times more compute to get to the like lowest number. To reach parity, we require around 40 times more compute. So
you do that despite the fact that you have different MIG precision.
Yes, right. So one of the cool things is that yes, so backprop we use FP32, like just to try to keep it as standard as vanilla as possible. With Eggroll, with the egg model, we do everything in integer data types only, including all the loss calculations and all of the layer norms and stuff like that. We do literally everything in integer data types, kind of in anticipation for a potential chip that might come in the future where floating point operations are just not used. And everything is done with integer operations. There's a couple of benefits to using integer-only operations, like the fact that everything is like associativity is actually preserved, versus like in floating point numbers, like yeah, everything is uncertain because of lack of associativity. And like yeah, so yeah, that's one of the cool results of this algorithm. And then we also tested like, okay, as data batch size increases, we see like some quite interesting results in which like after a certain population size, increasing the amount of data we put in doesn't actually matter. But if we want to increase population size, we also need to increase data kind of in parallel to get the most out of this. So we still haven't really like saturated what like the implications of Eggroll at this point. But yeah, there's a ton of other results. Like we showed how we can train a finance model to optimize profit directly end to end. We have a couple more like reasoning experiments, more LLM experiments and stuff like that in the paper, but I'll leave it to you guys to read it afterwards. Cool. And then there's a bunch of future work like trying to tackle sample inefficiency in kind of the RL settings, because we think of Eggroll as a backprop replacement, not as an RL replacement. So you can actually still use RL algorithms, but just use Eggroll instead of backprop as the optimizer. And then, yeah, we can also do model-based Eggroll, kind of training stuff on device to be able to, using the same capabilities and same chips needed for inference. Neurosymbolic architectures, non-differentiable objectives. One of our collaborators has worked on sparse autoencoders and mechanistic interpretability for training. And then also like new optimizers for Eggroll, because we've seen that Atom has kind of been developed with backprop in mind. We're trying to see like, is something new better for egg roll? Cool. Yeah. So our website is eshyperscale.github.io.
Okay.
If we have some minutes, then we can take questions.
Thank you. That was a great talk for a kickstart to our brains right after the meal. So I have a lot of questions. Any of you, if you have questions, please. I'll start with the one that. So you do this on multiple GPUs.
Yes.
So what is the multi-GPU strategy then when you do rank 1 updates?
Good question. So what we do, and part of this is because of the oddities of the Isambard framework, we had some weird JAX errors. So we just do only internet communication. So we actually deleted all the NCCL communication paradigms. And what we do is we share fitness. We only share the fitness scores at the end.
Yeah.
We only communicate fitness, and I guess everybody already knows what the PRNG keys are. And we let each device reconstruct the rank 1 updates themselves. So it requires very, very little communication. Instead of sending like basically terabits of data across all of the GPUs, we only send like basically kilobits of data saying like, oh, this is how good. Like I had like each GPU has like 1,000 population size, and you have like 100 GPUs. Like 1,000 times 100, and then basically everybody communicates each other's fitnesses, and then each GPU reconstructs all the rank 1 updates. And there's a quite efficient way of doing this fitness weighted average.
So if you do a higher size update, then you would have much more communication.
So as population size increases, then yeah, communication does increase. But it's always like small enough that it doesn't end up mattering. Whereas like with backprop based training, it scales with the size of the model itself, right? So we can actually train like, it doesn't matter if we're training like a 1 billion parameter model or a 100 billion parameter model. The communication that we need is still quite small.
Yeah. So what is amazing results compared to the baseline and state-of-the-art algorithms. So do you have any, the minimum size of the model that we should work with your model, your method, so that we can efficiently use your method?
Yeah, so when I first did my experiments on egg roll, I had a single 3080 GPU, and I was training a 0.1 billion parameter model. And that's where I saw the first sign of life. And I like messaged like Shimon and Jacob, say like, guys, I think we need to like do this for the Isambard grant. So this works at basically any model size, pretty much. We're still trying to figure out like, are there scaling laws in terms of as model size increases, how does population size need to change? What we've seen is that we can actually get relatively stable results across model sizes in terms of like getting stable learning. But it's still like active work in progress, and there's going to be like I guess a period of frontier in terms of like how what's the minimum population size you can fit into your systems.
I don't know how hard evolution strategies to mathematical analysis to prove all these results, but I think it's not that easy.
Yeah, so evolution strategies by itself is, I guess, quite straightforward. Like I could kind of derive it from scratch, but then when egg roll comes in, it becomes very difficult because it's no longer it no longer has a density function per se, because you're restricted to only rank 1. Yeah, like this equation, right? We can't do this anymore if we're only restricted to rank 1 updates. One of the key insights of egg roll is, despite taking rank 1 perturbations, we end up with a full rank update if you have a large enough population size. But we still need to like do a bunch of approximations to find out exactly what it is. So like Matty, who is the second author of the paper, he led all the theory. I basically said like, okay, I found this really cool algorithm. It works empirically. It scales very well, and it's hardware efficient. I have no idea if this is the correct update to do, or if there's like anything meaningful from a theoretical sense. And what he found is that like actually, as dimensionality of the model increases, there's something called the Gaussian annulus theorem, which says that like as dimensionality increases, instead of looking like a typical Gaussian where it's like kind of fuzzy in the middle and then things go to the side, at high dimensions there's actually like a kind of an annulus. There's kind of like a sphere that's like doesn't have anything in the inside, right? So actually, because of this, he was able to prove a theorem saying that, like, okay, if you're able to kind of constrain the noise scale correctly, this actually converges to the same update as evolution strategies, which was quite cool and unexpected.
Hey, nice to meet you all. My name is Junyuan Hu. I'm currently an assistant professor in robotics at the Department of Computer Science at Durham University. Today, I'm going to introduce a topic about cooperative learning and control in swarm robotics. So in this talk, I will just briefly introduce how control and learning techniques will be used in robotics application, especially when we have a team of the robots which need cooperation. Okay. Okay, so here's the main contents of my talk. So firstly, I will have a brief introduction about the research area in of swarm robotics, and then I will introduce two main different research in the multi-robot system. The first one is about the formation control, and the second one is about the swarm trajectory planning for UAVs. And finally, I will just briefly discuss how such techniques can be applied to large-scale energy system monitoring as the next step of my research. So firstly, let's start with the nature collective behaviors. So we can see that there are lots of intelligent swarm behaviors in the nature, like bird flock, fish school, bee colony, and sheep flock. So as you can see that when a team or a swarm of the animals are staying together, they could generate a high level of intelligence. So now the question is how we can learn from those behaviors or decisions in those animals and then apply such intelligence to the robots. So in the end, by using such swarm intelligence oriented approaches, the robotic teams can also be very helpful and intelligent in many real-world applications. So that is mainly about the motivation of doing research in the area of swarm robotics. So when we talk about swarm robotics, actually a brief definition is just to coordinate multiple robots. And for each of the robot, it doesn't need to be very strong. It can be very simple. It can only have limited capacities. But the main goal is now we just need to design a brain for a collective of them, such that in the end, they could also solve complicated tasks. So in order to coordinate them, in general, we may classify the approaches into centralized approach or distributed approach. So apparently, in the centralized system, we have one control unit to coordinate all of them. But the issue is this may not be applied to large scale of robotic systems because in that case, we may have a huge communication costs. So in order to solve the large scale robot coordination problem, we mainly rely on the distributed system such that for each robot, they just need to communicate with their neighbors. In the end, they can still accomplish the whole task. Okay, so there are already many applications of the multi-robot system. So for example, in the intelligent transportation system, each autonomous vehicle can be viewed as a robot, and through the V2V communication networks, we could apply swarm robotic control algorithm to improve the overall traffic efficiency. Similarly, we have the spacecraft formation flying, or we may deploy a team of the UAVs or ground robots for group and weed management in precision agriculture. And in the end, a swarm of UAVs equipped with the sensors can also be used for inspection or search and rescue in unknown environment. So now comes to our topic. So in order to develop such intelligent and cooperative robots in real-world applications, we need some techniques from different domains. One of it is, of course, the artificial intelligence, which include machine learning, deep learning, or reinforcement learning. So that is one of our main focus. Besides AI-based techniques, so we may also rely on the control techniques. So, for example, the distributed control or robust adaptive control or multi-agent control. So the main difference between the learning-based algorithm and the control-based algorithm is like the learning is mainly based on the data or the analysis, but sometimes it still depends on the black box. We may not know what's going on, whether it's going right or wrong. But for the control algorithm, it's based on the model-based analysis. So we may we may understand better based on the systematic analysis. So of course, if we can achieve the best of both worlds by combining learning with control, then we may be able to develop an even stronger approach to coordinate cooperative robots. Okay. Yes. So now, if we can apply or improve the learning-based or control-based algorithm for the swarm robotics, and then we have many different directions to explore, which include the robotic networks or the swarm intelligence and the connected vehicles. So next, I will start with one of the very fundamental topics in the multi-robot control systems. It's called formation control. So formation control is a kind of control algorithm such that a team of the robots can maintain a designed pattern via the local communication or information sharing. There are two different objectives. The first objective is, of course, the team of the robots need to form the desired formation from any initial positions. And the second objective is that they need, for the followers, they need to follow the leaders. And for all the robots in the team, they should have the capacity of avoiding some obstacles. So in one of my previous works, I developed a cluster formation containment framework to coordinate multi-robot system. So we may simply divide a multi-robot system into different layers. Based on, so currently we can assume that we have multiple targets in the environment, and then in the first layer we have the leader robots, and for the second layer we have the follower robots. And so we have several sub-objectives of this framework. Firstly, we hope that the leader robots could autonomously cluster into different subgroups just to track different targets. And secondly, we also hope that the leader robots could form a desired formation. And last but not the least, we aim to develop a containment algorithm such that the followers could converge into the convex hub formed by those of the leaders. So based on this framework, a number of the robotic control problems can be viewed as special cases of this framework, which include, let's say, formation control, containment control, or clustering control, or reservoirs, let's say. Okay. So in order to achieve this, so firstly, let's look at the autonomous clustering process. So this can be achieved by developing a game theory-based clustering algorithm. So the main idea is for the leader robots, they need to decide which cluster to belong to. Currently, based on the developed algorithm, the leader robots were mainly based on the two different priorities. The first one is the priority of the target. As you can see from the examples on the right. Yeah, so here, so you can see we have 5 different targets, and the size of a target means depends on the different priority of the target. For example, if a target looks bigger, means this target will have a higher priority than the smaller target. And the second criteria is depends on the relevant distance between the leaders and the closest target. So by considering both the constraints, in the end, based on the proposed clustering algorithm, the leader robots will achieve a stable cluster, as you can see in the last figure on the right. And once the cluster can be achieved, so now the next step is to for the adaptive formation tracking. So in this work, we proposed an adaptive protocol such that a desired formation can be achieved by the local information. So in this example, we have 8 UAVs, and the desired formation is a cube formation. And as you can see that just by defining the formation reference signal and by using this adaptive and decentralized protocol, the leaders could just reach the desired formation autonomously. And in the end, based on similar technology, the followers may also be able to converge into the convex hub formed by those leaders. So in the example I show here, we have a target, which is a small drone on the top, and we have 6 leaders. They can form such a safe area, and then based on this containment control algorithm, the followers will just reach inside of this convex hub. So this can be so these kind of techniques can be used in many applications. I will later show some of them. And last but not the least, the artificial potential field-based algorithm is implemented for collision avoidance, such that the whole robotic team will be safe in a cluttered environment. So the main idea is we assume that each robot is covered by a virtual force. So if there are other robots or obstacles inside of this virtual potential field, there will be a repulsive force generated to push the robot away from the collisions. Now, by combining all of them, now we have all what we need. So the last step is just to test whether everything will work in the real world scenario. So in this case, we have the robotic platform called Mona, which is small scale mobile robots. And we have this random configuration, which include a host computer and the camera. The camera will just detect the position of all the robots and only send to the host computer. And then the computer will only send the relative position informations to the robot, such that for each of the robots, it will only receive the local information rather than the global information. And this is the hardware closed loop control loop. So which also indicates the communication networks and these. So based on the experiment setup and the developed formation containment framework, a lot of tasks can be done using this framework. For example, in the target enclosing task, we have 3 different targets, and the 6 mobile robots could be divided into 2 subgroups autonomously, and then they can form a circular time variant formation around the target. And secondly, the robot can also form such a cage around the objects and start pushing the object. So as you can see that although the robotic platform we use is very simple, but when they are together, they can still do some tasks for us. Similarly, we have the formation containment, triangle formation, or for tolerance. So in the last case, the main idea is if at the beginning, the desired formation is a square formation. However, we assume that one of the robots stopped working due to malfunctioning, and then you can see that later the remaining 3 robots can still form a triangle formation to continue the task. If we can combine some of them together, of course, we can use this robot for some more complex problems. And so firstly, it's a search and rescue problem. So the robot can form. So we have some lost robots represented by the green tag. And we have some rescue robots by the white tags. So the idea is firstly, the white robots as rescuers, they can form a safe region because they will be, we assume that they are equipped with the collision avoidance sensors, but we are also assume that the lost robots may not be equipped with such sensors to avoid the collisions. So the safest way is that for the rescue robots, they form such a safe zone for the lost robots, and based on the containment protocol, the lost robots will automatically converge into that safe zone. So in the end, all the rescuers could send the lost robots towards the desired goal. And in the second case, it's a swarm sheep herding task. We assume that the white robots are sheep and the green robots are dog. So you can see that. So the dog firstly move behind the sheep flock and then start pushing the sheep, just like the real sheep herding task. So this is kind of a bio-inspired approach in swarm robotics, and as shown in some other simulations and experiments, we can use a team of the UAVs for target monitoring. We can also send a team of the robots for cooperative exploration. So in this work, we developed such a deep reinforcement learning based algorithm for exploration. So firstly, we generate such a well-known based partition such that although we may have multiple robots, we try to minimum their overlapping area, and then based on the deep reinforcement learning algorithm, the robot could just explore all the unknown environment autonomously and efficiently. So in the last case, as I said, if we treat autonomous vehicle as a robot, then we can also develop such autonomous vehicle platooning algorithm, such that in this case, we have a leader vehicle moving with a constant speed, while we also have 2 follower vehicles to keep the same certain distance among each other. Okay, so that's about formation control. So now let's move one step forward. Now assume that now we need to deploy some robots in the complex environment, and how the robots could decide a suitable path to follow, while also by considering the safety and the efficiency. So in these 2 examples, we try to explore these questions by considering the cluttered environment. So in the first case, it's based on the leader-follower swarm formation algorithm, and you can see that the robots they are able to form a different formation in such an algorithm, in such an environment autonomously, such that in the end they won't collide with any obstacles. And in the second case, it's we try to combine the RT-based path planning algorithm with the artificial potential field method, and again such a combination could achieve a better efficiency in the multi-robot navigation problem. And beyond that, we also developed such a time-optimal swarm trajectory planning algorithm. So different from previous case, so in this work, the time optimality is one of our main concern. We hope that the formation or the cooperative navigation of the UAVs not only achieves stable or safe behaviors, but also achieve a very fast behavior. So this is the overall objectives. And so in order to achieve this, of course, we need to analyze the UAV model. So I won't spend time on this, but later you may just check our publication for details. And the main idea is we have the time optimal control based on solving the cost function, such that we can achieve agile or fast navigation for the UAVs. So this is mainly for the single UAV. We have the reference trajectory planner to let the UAV avoid the obstacle while also finding the shortest path to save the time. And then later, once we have multiple robots or UAVs, we may rely on the flocking control algorithm here. And so this is also based on the virtual force. So in the end, by combining the time optimal planning and the flocking control a swarm of the UAVs, they could quickly navigate through a collected environment. So these are some simulations. So in this simulation, we have 9 UAVs in this environment, and you can see that there are some obstacles here and there. The overall trajectory are shown here. We also compared the overall performance with some other algorithm, are the state of art. And in the end, we found that our proposed planner called T-star outperform all of them. And not only about that, we also record a very short video in our lab. So we manually build this challenging scenario for these 3 UAVs, and as you can see that this won't be a big issue for our planner. And all these 3 UAVs, they can form the desired formation while navigating through them. Okay, so lastly, so last year we also have developed a new research about applying deep reinforcement learning for decentralized navigation. So the main idea of this work is just to develop such a door head soft active critic algorithm for the multi-robot navigation. So these approaches obviously can be applied to the warehouses, especially when we are trying to use the robots for the object transportation. So here I will just briefly introduce the main idea of this approach. So for each of the robots, they have several different observation channels, and they also have several actions. For example, moving left, right, up or down. And so for each of the robot, it need to consider the obstacle in the environment. It need to consider the other agents and the goal position. And so later we develop such a network structure. So firstly, the network structure is shown here. And we have the observation encoder and the temporal module as shown here. And then we also have the communication block on the right-hand side. And later we have the actor and critic head. So since we have 2 different head at the same time, so we call this dual head SAC structure. And sometimes the robot may also enter the deadlock situation. So in order to avoid such a deadlock in the multi-robot coordination problem, so we also proposed such an advanced escape policy, such that the deadlock, once the deadlock is detected, this will be used to ensure that no deadlock will happen. All right, so later we have conducted several experiments just based on the different size of the robots or different density of the environment. And we also compared the overall performance of our algorithm with some other state-of-art algorithm. So first case is we tested them in the random maps with different density of the obstacles. And secondly, similar experiment has also been done on the structured map with different number of agents. So here are the videos of both cases. So in this case, the goal position is represented by the green color, and the position of the robot is by the red color. And in the structure map, we choose then 312D, which is a more realistic map. Yeah. Okay, so finally, it's achieved. Okay, so of course, this kind of simulation results already verify the effectiveness of the proposed algorithm, but yeah, we still want to see whether it is feasible in real world scenarios. So later we also test, we also implement such an architecture to our drones in our lab. And here is the real world scenario results.
Do they talk to each other as well?
Oh, yes, of course. So they need to share the position information in order to achieve this kind of navigation. Otherwise, we can, if they are just independent, we cannot ensure that the overall efficiency of the exploration task. So communication is a very important factor in all of these works I introduced so far. Okay. So yeah, considering the time, I will just briefly introduce how we can also apply such robots or techniques to large-scale energy system monitoring. So this can be viewed as a future work, because previously I mainly focused on some experiments to show that yes, a team of the robot can really do something. But someone may ask, okay, so then what's next? So this is next. So imagine that now the UK has already have the net zero strategy. So how robotics and AI techniques can be applied for net zero or a sustainable future? So one of the applications is we can send a swarm or a team of the robots for the large-scale energy system monitoring, like the wind farm, because at the moment we are still sending some people for there, which may have some health and safety risks. And some of the companies, they may use manually control the drone for the inspection, but that is not very efficient, because when you have a large wind farm, if you just inspect them one by one, it will take a long time. But now, based on the such decentralized and cooperative system, a team of the drones, they can do these tasks autonomously for us. So now everything is just based on the proper analysis and system integration. And of course, all of them cannot be done without the advanced learning or control algorithm. Okay. I think that's all about my task. Happy for any questions.
Thank you, Julian. The audience is going to ask to what extent deep learning can be, I wondered, deep reinforcement learning can be used instead of the classical control theory, because majority of your work involves the classical control theory. And why?
Okay, yes. So thanks for the questions. Of course, because my PhD is mainly from the classic motion planning and the control side. So that's why. So the majority of work is focused on the classical or traditional control of a robotic system. However, recently the deep learning or reinforcement learning also play a very important role in such applications. So one of the things that classical control cannot be solved properly is the uncertain environment or the uncertain dynamics of the robots, because all these kind of classic control, they rely on the very accurate analysis of the system model, the very accurate environment setup. But in reality, the dynamics of the robot may be affected by some some different factors like model uncertainties or disturbances. So in that case, if we can develop a suitable deep reinforcement learning algorithm, then it may increase certain robustness to the overall system. And besides that, the traditional control algorithm also mainly focus on the if the task is very specific, or for example, we have a target, you need to follow it, or we have a trajectory, you need to follow it. But for the decision-making part, the deep reinforcement learning or the reinforcement learning algorithm may play a more important role, in my opinion. So it may help the robot to decide whether I should do this or not, rather than simply follow the road, or or once the decision is made, then the next step can be controlled. So it's good to use, to combine both the learning and the control into a single system, such that we will have best of both worlds. For example, we can use deep reinforcement learning as a high-level decision-making layer to make a suitable decision first. And then once a certain decision has already been made, we use a very reliable control algorithm or system to ensure that this task can be achieved. So overall, such combination will improve the overall robustness.
Reliable is the keyword. I think for the initial problems, would you use deep reinforcement learning, for example? Which one would be more reliable in that case?
It all depends. For example, if a decision is not directly linked to safety issue, then of course I would happy to use the learning-based algorithm just to help us to find a suitable decision. Well, if you really want to ensure the safety, like for example in the obstacle avoidance case or some similar, so in that case, I would prefer some control algorithm because
what is about? You do the computation on the robot, right? So what's the processor? Your model size is also limited by the processor capability.
So it depends. It depends. For example, with the increase in the computational power of the robot, so currently we can implement some high power, more powerful processor on the robot. On the other hand, we may still rely on, for example, the host computer or laptop as the main processor for the robot, and then we just send the decide actions for the robot, such that for each of the robots, they just need to take care of their own sensing or actuation, but the main decision making or computation can be done on the computer. So in that case, we may still achieve it.
Thank you.
Okay.
I guess I'm wondering, I have a similar question. On the communication end, do you think that we're still very far away from using deep reinforcement learning for end-to-end learning of communication?
Mm-hmm.
Because that's something that I've tried out a lot, and it seems like that's quite far away. Just wanted to see your opinion.
Yes, I agree with you. In most of my works, we just don't touch a lot with the communication side because we are not expert in the area of communication. I know there are some group of people, they have done a lot of research on communication, but since our main advantage is not communication side, so we may simply assume that, okay, look, so in this problem, we assume that the robot can communicate with their neighbors within a sensing range, and in that case, they can share some kind of local information with their neighbors, like the current position or the current velocity. And then our main focus is how each of the robots can properly use those information in order to achieve the collaboration. So that will make the problem simplified. But in the future, of course, we may also consider how the communication can be achieved. But that is, I think, another layer of the problem.
Thank you. If you do it in the...
Okay.
Yeah, so I'm from Imperial College in London. I'm in the aerodynamics department there. So I worked on this with Sylvain Lazette and George, and then also Max Weisenbecker in the maths department as well. And this is part of a AI for Net Zero project that we did. So the project had a number of different areas. We had kind of this wind farm control stuff, but we also had kind of digital twins for energy and transport, so hydrogen energy, drag reduction on vehicles, as a number of different areas that we're looking at. So I'm going to explain a bit kind of the background behind this, because I know we've got people from quite a lot of different areas here, and then some of the results that we got. So first of all, this is a kind of nice picture of a wind farm, and it shows quite nicely one of the problems that you have with these large wind farms where you have lots of wind turbines altogether. And you can see with this nice cloud structure that the wind turbines at the front are creating wakes in the wind where we have reduced wind speed and kind of more turbulent airflow. And this then propagates downstream, and the turbines behind kind of operating in those wakes conditions where they have less than optimum wind conditions. And this then compounds as you go further downstream. You add more wind turbines to your wind farm, the wakes get stronger, and your wind farm kind of efficiency drops. So you're generating less power output than you might expect from your wind farm. So one thing that you can do to try and mitigate this is you can offset your wind turbine. So normally you would operate a wind turbine pointing directly into the wind, because that would get you the kind of most power. But in some scenarios, what you might do is you might angle your wind turbine, offset it from the wind direction. This deflects the wake to the side slightly, and exposes downstream turbines to more airflow. So the front wind turbine is generating less power output. The downstream wind turbine would kind of produce more power output, and overall in your wind farm you get an increased power output. So this is a strategy that's quite well known. And then, so if you adjust all of your wind turbine wakes slightly in your wind farm, you've really got an optimization problem where you're looking to find the optimum yaw angle for all of your wind turbines to maximize the power output averaged over the time of your wind farm. So that's just a kind of optimization problem that we have. And you can see how this kind of works in a simulated environment. So here we have a simulation of 4 wind turbines. The wind turbines at the front are creating this wake that travels downstream, and then we have wind turbines operating in those wake conditions. You can see here the 2 turbines at the front. The one on the right is actually yawed slightly. So when we have this overhead view, you can see it's got an angle on it, and that pushes the wake over to the right. And that actually exposes the second turbine here to more of the kind of free stream wind conditions. And so that's the one that's generating that increased power output. So we want to work on trying to find that optimum. We do that in our work in a simulated environment. So for this work, we use the XCompact 3D, which is the DNS and LES flow solver kind of developed by Sylvan and others. It's a 6th order finite difference flow solver, 6th order in space, 4th order in time, using FFT to solve the pressure Poisson equation in spectral space, and it has a nice pencil structure to do the domain deconstruction that allows it to parallelize very nicely. And kind of importantly for us, it has a few different wind turbine modeling capabilities. So for wind turbine modeling, one approach you can do is use the resolved geometry. So take geometry and add it into your off the wind turbine and add it into your flow domain. To simplify that, because that takes a lot of computational power to do, what is often done is use an actuator line method, and this kind of decomposes the wind turbine into these different lines, and then we add forces to the equations kind of along these lines that correspond to the aerodynamic kind of lookup tables of the forces for different wind conditions along the length of the blade. So we kind of change the force along the length of the blade and then rotate the blades around. So we add that forcing term to our equations. And another method is the actuated disk method, and this just uses kind of a porous disk approach within the flow domain. So rather than resolving the kind of moving location of the wind turbine blades, we just say each wind turbine has kind of the same effect as a porous disk on the flow, especially when you go downstream, and the effects on the downstream turbines. So in XCompact 3D, we can do the actuator line, actuator disk methods to model these turbines. And so what you get from this is here's a fine LES simulation of using actuator line method, and this is just a slice through the domain of the flow field that you get. When we coarsen the LES simulation and use an actuated disk model, we don't catch all the same number of scales as we do in the fine simulation, but the downstream wake dynamics kind of match quite nicely. And there are other methods. So a lot of people use, for kind of optimization approaches, these simpler analytical wake model approaches, where you just have an analytical model of the wake downstream. The problem with these is most of them don't capture the dynamics of the turbulence and the wind that is happening. The advantage is they're very cheap to run, so you can kind of integrate them into optimization strategies. But because they don't capture those dynamics, they're not so useful in some cases, which we'll show. And so we're going to focus kind of in this work on using the actuated disk method for optimization and control kind of approaches. So we take a simplified problem of a wind farm, just 3 wind turbines in a line, aligned with the kind of wind direction. And we're looking to do this optimization problem by maximizing that power output from these 3 wind turbines, adjusting the 3 yaw angles of the wind turbines. So we take this flow field, we run a simulation of this case, and then a standard approach would be to do some Bayesian optimization. So we wanted to find those optimum yaw angles. So we did that here. We ran a Bayesian optimization, and we get yaw angles of 20 degrees for the first turbine, 13 degrees for the second turbine, and then -3 degrees for the third turbine. And that gives us a kind of roughly 2% power increase in that wind farm. So that it's fairly small, for particularly what you expect from a small wind farm with only 3 wind turbines. But yeah, even a small increase in power output is quite beneficial for these wind farms.
Do you use to extrapolate this to multiple wind turbines, or it's just for 3?
So in this case, we just done this for 3. We've done it before with deeper wind turbines for this kind of optimization, so up to 10 wind turbines. And when you do that, you see the power improvement really kind of grows a lot more. So we get kind of like 10-15% power improvement when you kind of increase to much deeper wind farms. But in this case, we've just been looking at this 3 wind turbines as a first kind of setup. So we can find this condition where you angle them. And you can see here with these 3, you see with the flow, the first wind turbine is kind of, the wake is pushed to the side slightly in the mean flow, and that's what's kind of allowing us to generate more power output. Yeah, so if we look at the power output, if we compare the kind of greedy case, which is the standard pointing directly at the wind case, a static optimization, Bayesian optimization approach can give us a kind of a mean power improvement that we see before of 2%. If we look at the instantaneous farm power, the distribution of that, we actually kind of shift that. So we particularly find that we're operating more in these higher power output conditions, and the kind of peak here drops slightly, and then the low conditions kind of match quite similarly. So that's kind of where that power is coming from. One thing you might notice is if we look at kind of this distribution of the mean power outputs, we still get some cases where we really have not much power improvement at all. So we kind of wanted to understand that and try and improve that. And so this comes from a lot of this kind of time averaging that we're doing. So when we do the Bayesian optimization, we're looking at the mean power improvement over a amount of time. So as we average that simulation, actually again, as we average it, we go from that instantaneous into that kind of mean flow field condition, and that's what we're kind of optimizing for. This, if we look at the amount of time it takes to get a nice average, so here a relative variability of the mean power improvement kind of down below 5% is like it's 1,000 hours of runtime. So this is going on for a month of simulated time for a wind turbine operating, and that's for this one flow condition. So there's a mismatch there between the optimization result being in this mean field and this mean kind of condition that we're looking at, and the conditions that it experiences which are far from mean. If we look at the kind of inflow that we use for this, we use an atmospheric boundary layer. So this is the kind of flow field that you'd get out at sea. There's a neutral boundary layer, so maybe kind of in the evening you get something like this. And this, you can see there's a lot of variability in the kind of wind speed, as you see on the right here. And the structures are really kind of maintained in that flow field for a very long amount of time. So you might have a structure here that has a higher wind speed that kind of your wind turbine is sitting half in, and that kind of can change what the optimization is. That's where that variability is coming from. So one thing you can do is you can look at changing that wind direction. So if you change that wind direction, you might have a different optimum. And then you can, so we run optimizations for a whole range of different wind conditions. So here ranging from -10 to 10 degrees offset of the wind direction, find all these different optimums, and then use that in a controller so that you adjust the yaw angle based on that kind of instantaneous wind condition direction. And we find a moderate improvement using this kind of dynamic phase optimization approach. But we think there's more. When we look at this, we see that even here, the controller design is still operating in that mean flow state. So we're still optimizing in a mean flow condition. We're just applying it to this instantaneous flow field with these turbulent features. And we're just taking a single wind direction parameter and setting the angles based on that. And there's a lot more information in this instantaneous turbulent flow field that we could exploit to try and improve our control operation. And so, yeah, so our controller design is not the same as the control operation in this case. So what we're going to do is try and introduce a dynamic learning, and we do that with reinforcement learning. So if we take our 3 wind turbine setup again, what we do is we want to take actions at different time steps for our 3 angles, and we do that based on the state of the flow field and the power output as a reward in a reinforcement learning loop. So we do this at 10-second intervals. So here our actions are going to be a differential controller for our yaw angle. So we look at changing the yaw velocity of the wind turbine, so just the speed it is turning at, rather than setting it exactly. The reward being the power output of total wind farm in an instantaneous way. And then the state is a combination of observations of the flow field, which we take as kind of probes throughout the flow field, and slice at the height of the wind turbine. This is kind of similar to what you might be able to get from kind of LiDAR systems that you can mount on top of wind turbines. So it's not exactly that, but it's kind of trying to represent what we might be able to get from real life data. And then we also give it as a state the angle of the wind turbines at the previous time step. And so we need to then look at, so go back here. These simulations are quite expensive to run, and reinforcement learning being kind of notoriously requiring a lot of data to train. We have a bit of a problem there. So we wanted to try and parallelize our simulations. So we want to run parallel environments. So we need to run multiple different simulations at the same time, and couple that with the reinforcement learning controller. So we have our LES code, XCompat 3D in Fortran, and the reinforcement learning controller in Python. And we also want to control multiple simulations at the same time with that. So to do that, we used SmartSim and SmartRedis, as this is a kind of in-memory database that contains our actions, our states, our reward, and allows us to control all of the kind of separate simulations at once. So at each step, we pass an action from the reinforcement learning through the SmartRedis database to the multiple parallel simulations running on separate nodes. In this case, we're running on Archer 2. And that then allows us to do that all in memory, so it doesn't slow anything down too much. And then we can also pass back the state and the reward from our simulation back to our controller so that it can learn what to do. So here I'll show you some of the training we did. So we used a soft actor critic controller, where we separate the actor and the critic out. And then we ran this in 32 parallel environments. We trained it for 2,000 episodes, each episode with 500 reinforcement learning iterations, and each reinforcement iteration had 50 simulation test sets. So it's quite a lot of steps to train it. When we did the training, you can see the kind of cross episode numbers. We initially get quite a large drop in the power output of the wind farm, but at some point it learns what to do. We go from negative into that positive improvement in our farm power output, and then it keeps on growing up there at the end, in this case. So once we had it trained, we then run an evaluation, and this is kind of what it does in one evaluation. So you can see the line here, that the top shows 3 different yaw angles, and the bottom shows the power output of the wind farm. And you can see how the wind turbines are kind of adjusting their angle based on the flow conditions around them. Yeah, so there's a few things that we picked up from this, but I'll explain them more going on. And you can see here, so particularly the red line here, you can see it switches quite often from kind of a negative yaw or positive yaw angle to a negative yaw angle, fluctuates around, switches back. The second turbine kind of mirrors that, but with a lower amplitude, and the third turbine kind of does the opposite bit. So we wanted to kind of understand this a bit more. So we ran the evaluation out for the 2,000 steps, and then we did that 224 times to try and generate some statistics from this. So first of all, the power improvement. With the reinforcement learning, we see another step up in the power output from our wind farm. So that's the kind of first good result, is we're generating more power output. So we think we're doing something that's better than just that dynamic control that we found before. It's kind of nearly twice as good as when we did a static Bayesian optimization. And you can see again in the distribution of the instantaneous, we can do the same. We shift the more those high power output conditions. We then wanted to kind of understand what it's doing. So it's very well, it generates more power output from the wind farm, but we want to understand why it was doing that. So we looked at the correlation between the wind turbine angles. So here between the first and second, and then the second and third. If we plot those throughout the different evaluations, we can then get a distribution of kind of the correlation between the angles. And you can see here it kind of clusters around 2 points. When you do an autocorrelation, you find that there's a time lag between the first and second wind turbine angles. So they match much more closely at a time lag that correlates with the time it takes for the winds to propagate from the first wind turbine to the second turbine. So it's learned that time lag, and that the first turbine does something, and then the second turbine does something at appropriate time period later. If we adjust for that, we can also see we get this nice kind of positive correlation and negative correlation between our first, second, and then second and third wind turbines that I kind of mentioned earlier. These red dots are the peaks of those, and the blue dots here are then the Bayesian results that we had from earlier. So they're kind of close to the Bayesian optimization results we were having. So they seem to be moving between those Bayesian optimization results in a positive and negative setting, with some other stuff thrown on top. So that's the first thing to understand. It's kind of movement between these different settings. We wanted to understand again why it's doing that. So we looked at where they. Well, this was a snapshot of the flow field, and we wanted to understand kind of how it's deciding which way to go. So we looked at plotting here the barycenter of the velocity in front of each turbine compared to the angle. So the barycenter is just when the wind is stronger on one side compared to the other side. So here we have a gust of high-speed wind on one side, and that then correlates to a negative barycenter. And then we get that cluster of, when we have that barycenter on that side, we tend to yaw in this direction here. And what that does is it pushes that high-speed wind towards the downstream wind turbines. So if we go a bit in time downstream, the first wind turbine is pushing that high speed towards the second, and the second is pushing that high speed towards the third. So this is a control mechanism that it's not been used before because it depends on that kind of understanding the turbulence. And the RL has kind of found that on its own, which is quite interesting. So it does that in both directions so that you get that positive kind of peak here, and then on the opposite side, when we have a gust on the other side, we get that negative one. It pushes it towards the wind turbines again. So just quickly, we also looked at the frequencies that the wind turbine was kind of actuating at, because we didn't want this to be unrealistic. So here we have, first of all, the dynamic Bayesian optimum. When we run that, the kind of frequency distribution of the yaw angles. When we do the reinforcement learning, we've got the higher peak here, but it's operating at a lower frequency than the kind of lookup table approach. So that's a good thing that we're of the peak of this is at a low frequency, so we don't actually have to yaw too fast. We then also tried limiting this. So we did some bandwidth limiting with a low pass filter, and actually a lot of the higher frequencies are not important at all. And so you can cut out all these high frequency kind of actions, and we kind of maintain the power output up into quite a low frequency. So that's another good thing for implementation, is that we can potentially just have quite slow yaw control and still get these gains. So just to summarize, we trained a dynamic wind farm controller in the LES environment with reinforcement learning, and this kind of gave us a controller that allows us to get twice the power improvement compared to just a static optimum based on the mean flow field. Yeah, so thank you.
Thank you, Andrew. Also, we saw the reinforcement learning for scientific discovery. I'll ask more questions, but one burning question before the session ends.
Several questions. Start with one. So in the turbine diagrams you showed in the experiment, they're all kind of linear, one after another. To what extent do you think that's optimal? And to what extent does it matter for UK net zero? Like, are all the wind turbines just there, so replacing optimization?
Well, yes, it does matter. When we looked at, so when we change the yaw angle of the wind, that's kind of similar to just offsetting the wind turbine slightly. So we looked at how that affects, and basically the optimum is close to when you get something like plus or minus 10 degrees wind change angle, and that then gives you you kind of go back to a greedy case of optimum. It will change based on the wind conditions and the different layouts and things. Yeah.
Do you have a sense of the mean optimum placement or something like that? Is that something?
So we didn't look at placement in this study. People have looked at optimizing placement. I think they tend to be laid out in a grid. I mean, yeah. You want them to be together because you don't want your cables to be too long. There are lots of different things to consider for placement. Yeah. In terms of dynamics, random placement works quite well when you look at optimizing it. But they all seem to be in grids. So.
Any other questions?
Yeah, I think it's a quick one. I was wondering why you were using Adam's dashboard. Assuming, like, since you mentioned that these simulations would be quite heavy and therefore they could be very bounded rather than using them with just keeping all this inaccuracy.
It's not something we looked at in study.
If you say that that was stronger, that would be heavier than the.
Yeah.
I was wondering if there was some kind of like some thought, if there was some thought behind it.
No, it's not. It was just the kind of default setting there. So,
Thank you.
Yeah, thank you all for the first hour. Thank you, Andrew, again. And I'll let you have more discussion during the coffee hour. We'll have the coffee in the roll now. so not Mountjoy, and then keynotes from UKRI about the compute roadmap in the UK. It's going to be in the computer science building, and then we're going to reconvene here. So
I think the coffee is also in the.
there's also move there.
So we don't have
Everything is
that.
there. Move there. Thank you.
Yes, my name is Shruti, and thanks, Scott, for the introduction. I'll be talking about work I've been doing over the last 9 months or so during my ENCODE AI for Science Fellowship, which is based at Cambridge. And all my work has been on reinforcement learning in science problems, and recently it's been focused on particular fluid mechanics problems, which brings me to the title of my talk. And I'll first present some background, the approach I'm taking, progress towards this, next steps, and some perspective on how these sorts of environments might be useful for advancing RL approaches in general. So in terms of the background, fluid flows are common. We see them pretty much everywhere in nature. So from Junior's talk in the morning, there are these collective behaviors that are apparent in birds flocking, things like that. On the left-hand side here, you have fish swimming, and their behavior is affected by flow patterns created by other fish, but also the currents in the water. And fluid flows are also important for engineering applications. So contrails, for instance, produced by aircraft, have a significant impact on global warming. And despite being pretty common and people studying them for a while, fluid flows remain difficult to predict and control. And that's not because we don't have a good model for some classes of fluid flows, like Andrew and others will be very familiar with conservation and mass and momentum for fluid flows. So this is essentially the two equations are saying that the amount of fluid going into a box is equal to the amount of fluid going out of a box, and the change of momentum inside this box is equal to the sum of forces on the surfaces of the box. And then we can make the box infinitely small, which gives us these differential equations over here. So these are the incompressible Navier-Stokes equations, which means that all the velocities here are much smaller than the speed of sound, where compressible effects come into play. And these equations, part of the difficulty with solving them is this nonlinear term highlighted in yellow. So the interactions essentially happen at multiple length scales in the flow, so from the largest scales up to the smallest scales, which are mediated by viscous effects. And with that, also, I'm happy to take discussion and questions throughout the talk. That might be more fun. It's a smallish room as well. Okay, so as we know, fluid flows affect weather and climate. I still don't know what the weather is going to be like next month on a hike in Switzerland, whether there will be another heat wave or not. And more long term, so in the next 80 years or so, there's a pretty huge uncertainty in sea levels on the Earth. And part of this is due to the melting of ice on land, and another part is due to the expansion of water in the ocean itself. And my work is motivated more by water expansion in the oceans. I'm not considering multi-phase effects. So if we look at a box of the ocean, and there's a surface profile at the bottom of the ocean, water coming and hitting the surface, producing waves. And then away from this surface, there are also interactions between different waves that are produced, and these are known as internal waves. So similar to waves on the surface of water that we see, including the pond or lake over there, we have internal waves. So I'll now talk about the approach I'm taking towards some of these fluid flows in the ocean. So I'm considering stratified shear flows. Stratified essentially means that the flow is layered in density, so we have less dense fluid on the top, denser fluid on the bottom, and this layering can be driven by temperature or density of salt, fraction of salt. And in general, we can call this buoyancy, and there's light fluid on top, heavier at the bottom. And shear flow essentially means that there's a gradient of velocity as we go across the depth of the flow as well. And that gives us another equation for the transport of this buoyancy term, which we can think of as temperature. And essentially there's a viscous component or a diffusion component here and an advection component over here. And for the purposes of this work, all these Roman letters are constant, so we don't need to worry about what they will do because they don't change and they're fixed. And we're more concerned with these variables that are changing. That's velocity and buoyancy. So considering a two-dimensional setup where we have a buoyancy profile and a velocity profile that we start with, this image essentially represents the initial condition for the flow. So we have lighter fluid on top for the buoyancy here, dense fluid at the bottom. The gradient is much sharper than this linear profile I've shown here. And same for the velocity. The gradient is sharper. This is a hyperbolic tangent profile. And then for the flow, there are additional quantities that describe the flow. So that's the vertical velocity and the vorticity, which is the curl of the velocity vector. So we have rotation shown in blue and yellow here. Okay, so the vertical velocity in this case starts with a small disturbance. The scale of this vertical velocity disturbance is much smaller than the other components of the flow, so it's a small disturbance that's evolving. And then we can see what happens. So there's an initial period, and then there's mixing of, say, the temperature profile here. So the blue and yellow mix a little bit to increase the range of the purple region. So that's the mixing in the flow. And overall, we have an initial perturbation, which is fairly small, and then the flow evolves subject to the governing equations. And the question is, can we get generalized mixing in this stratified shear flow setup? So to do this, I can add an additional small body force F to the momentum equation. And here I wrote down a functional form for F that I think is reasonable. And I'll see how it evolves. So K here is 1, which means actually in this case it's a fairly high frequency. So I'll see how this evolves. It's a similar sort of video. If we're not looking at them side by side, there's mixing that's produced, and the flow evolves under the initial conditions and this forcing term F. We now try to compare this. The approximate mixing region is shown by the yellow line over here. And in the unforced flow, we can see that the mixing is relatively less. So by just handcrafting some sort of forcing function that I thought was reasonable, and I don't even know that much about this particular class of flows, we get more mixing that's produced. Okay, so that gets us to an approach towards answering this question of can we get generalized mixing? And this is a classical reinforcement learning diagram where we have an environment that provides observations and rewards to an agent that executes actions in the environment, and then that repeats. The idea is that using this sequence of interactions, the agent might learn something about generalized mixing. So that's reinforcement learning for stratified shear flows. And the environment I'm using is a simulated stratified shear flow using Daedalus as the simulator. And the observations are flow field variables. So the observations here are velocity and buoyancy. The action is the momentum forcing F, and reward can be mixing efficiency, which I'll get into later. So the question is, can we learn F? And what should the reward be? The reward here is the dissipation of buoyancy gradients divided by the dissipation of velocity gradients, because the velocity gradients, the denominator is what's lost to the flow, so it can't be recovered again for mixing. And the mixing should be, it's defined as the irreversible component, so then this is defined as this calligraphic D with subscripts P and U, or for the buoyancy and velocity components, and this is spatial averaging, and that's what we want the agent to optimize for. And I can rearrange this by saying that if the overall return is G, the integral of the buoyancy dissipation minus G times the velocity dissipation is 0. And if the agent achieves a desired return, that is, and this term is then greater than 0, then that means this fraction is greater than the desired return. And that gives a different formulation compared to this numerator-denominator setup, which becomes a multi-objective problem. So this is a single objective problem, but it's a non-stationary one. So as an agent achieves the desired return, we can then increase the return and then see how well the agent does. Okay, so now I'm going to describe progress towards achieving this. And that's using examples from the literature. So reinforcement learning in fluid mechanics environments, largely if I look at the literature, and some of you, if you disagree, I'm happy to discuss, is largely the RL agent. What it does is for control problems from the RL perspective. But from the fluids perspective, the problem is, I would categorize it as navigation, control, or modeling. There's substantial amount of literature in navigation and control. So this example of navigation is an autonomous balloon that stayed up and maintained station in the atmosphere for over a month or so. And then control, this is in Rayleigh-Bénard convection. People have used reinforcement learning to both enhance and suppress heat transfer. So this is an example of enhancement. And modeling has typically been used to recover subgrid scale parameters that are sometimes known empirically. And the approach for stratified shear flows, I would say, is somewhere between control and modeling. And I can validate the RL part of it separate from the environment part. So for the environment, I can look at flow between two fixed plates. So color represents temperature, dark is cold, light color is hot. And we have a hot plate at the bottom at fixed temperature, a cold plate at the top, and there's a linear profile initially. And we can also look at vorticity. So there's a flow setup between these two plates at high enough Rayleigh number, and this evolves into a roughly steady looking pattern. So there are some results from last year looking at heat transfer enhancement in this Rayleigh-Bénard convection setting, and the authors very nicely compressed their policy into an equation, and the policy is essentially the reinforcement learning agent is adding perturbations to this temperature profile at the bottom plate in a way that there is no net energy addition into the system, because that would be cheating. Okay, so the videos look like this. The plumes here are a bit sharper than without these additional perturbations.
So the goal is to improve the convection now.
Yeah, in this case. There are also other papers where the goal is to suppress the convection. Imagine that in general being kind of a goal condition setting as well, which I haven't seen. And the statistics obtained by the reinforcement learning agent can be summarized here, where the heat transfer enhancement at the bottom plate is on the vertical axis, and time is on the horizontal axis. So initially the flow is settling. The gray is the unforced flow, which has a heat transfer enhancement compared to conduction of about 10, and the forced flow is higher. So these are results that I obtained with the agent policy in the literature and the simulator using Daedalus. So that gives confidence in the environment part of it. And now I can describe the validation for the agent side of my setup. So this is navigation in a cellular flow environment, where the environment was originally described in this paper about 10 years ago. And there's a swimmer in a flow. The flow has a background velocity, and the swimmer has a fixed speed, but it can control its orientation. And the reward is a change in height, so the swimmer wants to go up. And the action is a preferred orientation. The observation, I added a position term, so the overall observation is the orientation of the swimmer, the vorticity of the flow, it's a two-dimensional flow, and some notion of the position of the swimmer. And a naive swimmer, if it wants to go up, will orient itself upwards to try to go up. And then a trained swimmer, this is what I trained using soft actor critic, and we have two swimmers that both start at the same initial position and orientation. The naive swimmer is shown in white, the trained swimmer in this greenish color that learns to navigate around these vertical structures to achieve the goal of going up, whereas in this case, the naive swimmer gets trapped in one of the vortices. And that's the overall trajectory, and the length scale is non-dimensionalized by the vortices, the gap between them. And we can initialize the swimmer to create a representative profile of what would happen at any location in this shaded box over here with any orientation between 0 and 2 pi, and get a bunch of different final positions. And the gain is a quantity which measures the displacement of the trained swimmer compared to the naive swimmer. So here there's a gain of 11, which means that the trained swimmers are doing relatively well compared to the naive swimmers, which on average kind of get stuck here. And okay, we can complete these trajectories as well. And this is for a particular set of parameters. So here, 0.3 means that the swimmer speed relative to the characteristic flow speed is 0.3, and psi is the alignment time scale. As we increase the alignment time scale, it means the swimmer takes longer to achieve its preferred orientation. And so as we decrease the swimmer strength, the swimmers have to navigate more around the edges of the vortices, and as we increase the swimmer strength here,
Oops. It's just the TV.
I can keep talking throughout though.
Yeah.
So as we increase the swimmer strength, at some point the vortices don't matter and the swimmers can just ignore them. So that's what the panel on the right would have shown. And the results I get are a bit better than the ones in the literature. That's because I'm using this deep reinforcement learning agent, whereas the original paper used tabular reinforcement learning agent using a sensible set of features. And why do I use the deep reinforcement learning agent? Because I need it for the stratified shear flow setting tabular won't do. Okay, so with that, we can go back to the original question of can we get generalized mixing in stratified shear flows. So now I allow a little bit of reinforcement learning in this setting through this term A naught, which can be controlled by the agent between 0 and some maximum. Here it's 5, still to keep the perturbation small. And this initial result I get is that the agent trained using soft actor critic with this observation being the flow field variables and momentum forcing does about 20% better at increasing the buoyancy dissipation than a random policy, and about 40% better than no action at all. But what I want to do next is increase the complexity of the action space, so allow more degrees of freedom here, so that the agent isn't just constantly trying to force the flow as much as possible, but learn something that looks more emergent and fancy. So that's the next set of work. So the perspective part of it here is some of these fluid flow environments can be used for challenges in reinforcement learning that people are working on as some sort of test bed. And some of this is grounded in this recent notion of the big world hypothesis that comes out of the reinforcement learning community, which says that there's a finite agent operating in a big world, which means that from the perspective of the agent, the environment is constantly evolving. Even if the world is fixed, if I keep going to new parts of it, for me, the world is changing. It also means that the environment is high dimensional, and any reasonable learning needs to take place from a limited number of samples because I cannot hope to see the whole world. And I think fluid flow environments can be interesting for studying this sort of stuff because we have an evolving environment in many types of fluid flows, particularly if we go to very high Reynolds numbers, but the underlying conservation equations in many flows remain the same to good approximation. And then we have these high dimensional environments, and people have studied them for a long time, which means sometimes we have good lower dimensional representations that can help serve as some sort of ground truth. And particularly in experimental contexts, learning needs to take place from a limited number of samples. So this can potentially be considered even in this Taylor-Green environment, where I had different swimmers in different flow configurations, but you can have an evolving Taylor-Green vortex environment, which is just decaying with the exponential of mu times t, which means over time the vortical strength is reducing, and therefore the optimal swimmer strategy you can imagine is interpolating between this swimmer that.
Sorry.
No,
Mass
no.
is still conserved, right?
Sorry?
Mass is still conserved.
Yeah. This is like a very simple fluid flow that happens to have an analytical solution, so it's kind of nice. And one of my collaborators at Vila in Montreal is studying this sort of stuff. So he's looking at empowerment, which is controllability that an agent has. And if we look at the vortex environment, he has this very nice result that shows in the middle of the vortex, the agent has relatively low empowerment. And at the edges, which is the part it's using to navigate, the empowerment is higher. And this stuff is without any notion of reward. This is just the agent exploring the environment. And so Jeremy thinks that empowerment can be a good good frame for informing models in model-based reinforcement learning. So that brings me to the end of my talk. I have code for a lot of this online already. And I'd like to thank ARIA, first of all, for funding all of the work over the last 9 months. And collaborators, so Keaton is the person who wrote a large part of Daedalus and nicely helps with some of the environment side, and Colin Coffey formulated the stratified shortcut problem. Yeah. Thank you.
Thank you. Any questions? Yeah.
Well, I have one
but I think it's gonna be quick. In one of the first 10 slides, I think you show a different way to embed the reward by making it like a boundary that keeps moving more and more your agent does better, roughly. I was wondering if if there was a specific reason for this compared to just saying, okay, I expect to get a given number for my G, and then I set it as a fixed number, and then I compute the reward as like how far I am from there.
Yeah, so if you know what you want G to be, then that works. And if you want this, so that's valid for some stuff. And then if we want to be in a setting where we say, can the agent achieve as high G as possible, then this non-stationary setting comes into play. Another way, my initial thought was to make it multi-objective. So to have this numerator be optimized and the denominator be optimized separately. But that was not so satisfying because the multi-objective framework doesn't distinguish between adding the two or subtracting the two and dividing the two. So I like the non-stationary.
I was asking this simply because I was wondering how the gradients behave.
I will tell you.
Okay, let's check more. Okay, fine. Well, thank you.
Any other questions? I'll ask one. When you said that did I understand correct? Emergent behaviors.
Yeah.
Right? So you meant that when you increase the number of parameters, you will see something that you discover through the reinforcement learning.
Yeah, it's essentially, so what's the strategy? So
closer to Andrew's thought over there again, they discovered something. But it was just observation, right?
Yeah, I think emergent maybe has a different meaning here. So in these flows in the ocean, people think that they behave very close to critical. And by emergent, I mean more if I allow certain degrees of freedom. If I go back to Andrew's talk, then he said, oh, how does this RL policy does better than the greedy policy? Right now, what I see is very close to the greedy policy. It's just to execute action all the time.
Yeah.
So it's more seeing something more sophisticated. Yeah.
And I'll ask another one. Some of these problems, I asked before the talk as well. I don't understand why you would pose it as a reinforcement learning problem, but not as an optimization problem, like the improving the mixing, for example.
Yeah.
It's just you have few parameters for those. You can pose this as an optimization problem. Is it something different than that?
You could, and then from my understanding is that for it to be posed as an optimization problem, the gradients essentially have to go through like the entire trajectory.
Yeah.
That's my understanding, and that is considered to be expensive.
I mean, there would be an alternative, like a stochastic optimization algorithm, where you wouldn't even take the grade, like evolution strategy, as Bilipta described. So you would have that kind of, but then in that case, you would need too many iterations. And I think, I don't know, how many iterations would you get with the reinforcement learning? Maybe it's similar.
Yeah, so right now it's model-free RL, so that's not going to be particularly on the very efficient side, and that's more the line of work with Jeremy and Doina at Mila. So that would consider model-based RL methods and then see if that stuff is efficient. But it's also possible so we might implement this adjoint-based stuff with Keaton and see how that actually compares to the RL approach. Yeah. From what I remember at the ORCO-FAC meeting a couple of years ago, actually, people saw, for whatever reasons, I don't know, that the RL policy was performing a bit better
than optimization
policies.
Yeah.
I don't know the details.
Yeah,
but
they still need to understand. We still need to understand the underlying reason. Mathematical explanations are needed in this case. So, any other questions? If not, let's thank Shruti again. Is Giorgio Maria Cavalazzi He's working with Professor Alfredo Pinelli at the City St. George's University of London. It's about, again, fluid dynamics. He'll systematically expose 3 structural pathologies in standard multi-agent reinforcement learning for turbulence control. These are reward hacking, credit assignment failures, and energy dishonest objectives. So it's pure reinforcement learning and CFD altogether. It's an interesting talk. So we'll see significant drag reduction. Would you consider it significant, 17%?
No, I wouldn't.
Okay.
Significant, but I'll get there.
Okay. So please welcome Georgie.
Good afternoon, everyone. Thanks for coming here, even if it's the last talk of the day. I will talk about computational fluid mechanics and reinforcement learning, but since we're here, I will also talk a bit about software and HPC, and I'll show how we choose to implement some reinforcement learning algorithms with the codes for CFD in some particular ways, so that it's not going to be just fluid mechanics, it's going to be a few other things. In fluid mechanics, there are plenty of problems, particularly when you deal with turbulence. And here I'm talking about a problem that Shruti before didn't mention, that is the near wall cycle. So for people that are not familiar with, in wall-bounded turbulent flows, there are some frameworks that explain how turbulence is generated close to the wall, and then how momentum and energy are redistributed far from the wall in a self-sustaining cycle. The idea is close to the wall, the velocity is 0, the gradients all the gradients are 0. How does the flow become turbulent? There are some coherent structures, a set of coherent structures that can be characterized. And apparently, some of these structures, particularly the longitudinal low-speed streaks, which are streaks, nothing too crazy to imagine, can directly be related to drag. So in the fluid mechanics community, there are plenty of people that try to tackle the generation of these particular structures as a surrogate to say to find a way to reduce drag in your channel, in your pipe, in whatever wall-bounded flow. The most classical and also simplest way to reduce drag by tackling the life cycle of these structures is called opposition control. Opposition control simply means that if you have a wall with a flow that is moving close to it, you change the boundary conditions for the wall normal velocity, and the wall normal velocity simply becomes the fluctuations of the wall normal velocity sampled at a given height from the wall. Non-dimensionalized units usually this is at 15, Z plus or Y plus, depending on the conventions, 15. You take these fluctuations, you change sign, and that becomes your boundary condition. By doing so, it's been proven in plenty of literature that you can thicken the Stokes layer where gradients are not too high yet, and basically push the generation of turbulence a bit upwards and decrease drag by doing so. Then, in recent years, I would say starting in the early 2000s, people tried to say, okay, this opposition control law is quite naive. With reinforcement learning or with deep learning and machine learning, we can think of doing better. And given that we can, in a CFD environment, we can observe more of what's going on, maybe we can find a policy to define blow-in instruction smarter or in a better way to achieve higher drag reduction. What I will show later is that the vast majority of the policies found here are either cheating or they are not feasible. But there are ways to not to throw away reinforcement learning for flow control at all and make it work. This is the concept of my talk. So first, let's talk about the CFD solver, because before starting this session, there were some people that were wondering how much of such cross-disciplinary code should be a black box, how much should you
should you write yourself? I'll show you what I did because I thought that after 4 years of my PhD thesis and many paths tried say this was the way to go. Oops. Okay. So we for the CFD solver we based our work on CANS, which is a freely available open source code developed by the team of Pedro Costa in depth. They did an amazing work, and this code is written in Fortran. Is highly parallelizable. It works with GPUs and CPUs as you want. Here I'll use the GPU-based version, which relies on OpenACC and Q.comp for the domain decomposition. And in this side, of course, we use a low storage Runge 3. And the partial solver is a highly optimized FFT-based one. So for everything that concerns the fluid dynamics, this is the code that we start with. And for everything that concerns instead the reinforcement learning, we built our reinforcement learning routines from scratch by using PyTorch. It's a simple multi-agent. We use as policy either DPG or TD3. We are showing the result with DPG, but the other ones are not particularly different. But what I want to show here is that these two words are separated mainly by, apart from the variables also, of course, but mainly by the language. Fluid dynamics is Fortran because we try to find Python codes to work faster than highly optimized Fortran code, and no way, even with the highest possible optimization levels that we can get. On the other hand, reinforcement learning is Python because no one, especially if you are a PhD student or if you are on a short contract, no one has time to write the routines from scratch in Fortran, especially if you want to invent something that is quite cutting edge without relying on external libraries like Torch or so. It is feasible, but I mean, you learn a lot, especially when you're a PhD by writing things this way. And this interface was highly optimized to keep everything on the GPU as much as you can expect. There are several ways, as you can imagine, to merge these two words. And the way we operated was taking CANS, the CFD solver, as it was, and make all the collective operations that are needed while using a CFD solver live in a different communicator. We called it CANS communicator, CANS-com, and then make this communicator talk via MPI with another communicator, which is one rank, one extra rank, which includes the Python process, the Python rank. So this means that we basically had to, it was just using grep a lot to edit CANS. It wasn't a big deal. It was compiling smoothly. We had to study a bit how communications between different processes work, because to be honest, it's not something so well documented because very few people do that. There are two paradigms to approach this kind of multi-process connection. One of them is using spawn. So you have a sort of parent-child or a master-slave, whatever you want to call it, structure, where you have one main process that spawns different processes as children. So these processes these processes struggle to interact with the parent. They interact very well with each other, and then whenever you need, you can find a way to make them communicate to Python. So Python in this way orchestrates everything. This is something that the admins of HPC systems hate. Like I had several discussions with the admin of our HPC system at City, because the spawn processes are seen like they look like someone that logged into your node and launch a process there without using the scheduler. So sometimes they are shut down. Sometimes you cannot shut them down easily because they are tied to other process. This is a mess. The way to go, we found out, was using multiple programs, multiple data structures that could be easily embedded in one Slurm call, and it's simply a difference loop call when you start one process and this process is aware that there is a communicator with other processes running, and you can make them talk to each other. This is well available in a GitHub repo that you can definitely have a look at, and you can also contact me if you have further information. And okay, so this is the structure of our interface. The intercom communicator to communicate between Python and Fortran is only used to send from Fortran to Python observations, rewards, and other flow quantities, and from Python to Fortran to the DNS, the actions, which are the boundary conditions that govern the flow. Simply, it's used just for these operations. All the other collective operations are taken care of by CANSCOM. Okay. In this slide I just explain a bit more into what are the variables shared. CANS shares the velocity values at y plus equal 15, as opposition control does, but we also have the streamwise velocity component and the pressure for further analysis. And the pressure gradient, that is the number that I currently need as a surrogate for the drag reduction. Bear in mind that if you have a constant flow, lower pressure gradient means that I need less energy to push the flow, and therefore there is less drag. This is quite common for fluid analysis, but I want to show to the audience, let's say. And Python simply sends back the whole normal velocity as boundary condition of the whole. Okay, so for I'm happy that someone before me explained a bit how reinforcement learning works. Here I just included this slide to explain how this specific kind of multi-agent reinforcement learning works. So there is you know that with reinforcement learning there's the actor and there's the critic. Here in this case, the actor is the critic is one big critic that sees the whole field and all the actions given, like there were two images. Then I'll explain later. We did something a bit more complicated, but take it as it is, like two images and the reward type. The actor instead only sees the flow above a tiny patch of above a rectangular patch, and that's it. But all the actors that contribute to make the whole surface that are controlled, the wall, all the actors share the same weight. This framework is called centralized training, because you train everything all together, decentralized execution. And the idea is that if you have periodic boundary conditions, and if you don't have phenomena that happen on so many different timescales, at least of the wall, you can get a much faster training. To make the training even faster, we train our agent on a smaller box, and then to run evaluations, we run evaluations on a much bigger one. The reason is that if you have a small box with periodic boundary condition and a low Reynolds number, just high enough to have a turbulent flow, if you have a policy that gives drag reduction, you may find yourself in a situation where the flow relinearizes. So you make, even for 1 second, you have a policy that works so well that it breaks one of the structures that you need to have this self-sustaining wall cycle, and then turbulence disappears. But this is not something that we want, because we know that in a channel flow or in a turbulent flow with a decent size, this will never happen. You'll always have some turbulence around, but you will never get a big box to linearize. But and it's good because you can get values of your policy, of your reward evaluated with much less variance, so that they are more precise and more reliable. Okay, I have a slide to explain this. So this is basically what happens in a small box, and this is what happens in a big box. if in a small box, by any chance, even at 1 second, one of these two streaks disappear, turbulence disappears after a few time steps. So that's why we have to be careful.
But don't you need any periodic boundary condition?
We do have
Despite that, you still lose the.
Yeah, especially for that, because if the blue streak becomes too big, then like you have the blue streak that interacts on both sides with the boundary condition, and it flattens after 10 minutes. Okay, so I promised that I would talk about how some people do in this field, and I want to highlight 3 main pathologies that are very common for this. This is what you see here. Like, it looks quite complicated, but this is the example of a policy map where you have on X one of the 2 components of the velocity, and on Y the other one, and the color represents the value, the local value for that patch for the boundary condition. Red means that I am flowing, blue means that I'm stuck in. What you can notice is that basically this policy is saturated. This policy is nothing else than a collapsed tonnage, which is what you have at the end of your actor. And this is very common in this field, that people present policies that are just saturated policies. Overlapped, you can see the probability density function of the velocity that is actually used as boundary condition. There are 3 levels to take 90%, 50%, and 25%. And what you can notice is that most of the events are concentrated around these 2 blobs. You can see these 2 blobs. This is, in jargon, this is called bang-bang policy, because what happens is that the actions given are just hitting the 2 extreme of your policy of your action space after each time step. Sometimes this works well to find a good reward in a fluid dynamics in a computational fluid dynamics context. But if this policy, like, people also show numbers of reduction that are pretty high, but then if you evaluate this policy on a bigger field where you don't have linearization or you don't have other problems, you get values that are not as high as 25%. They are indeed lower. These are the probability density function of the velocity at your classical 15. And this is to you can clearly see that it's still a bang-bang policy, because most of the events are concentrated around plus and minus 1. And this means that it's not only what happens at the wall, but also what happens inside the flow. This leads to a degenerate policy. Okay, so for the first thing that we should take care of is the mean subtraction projection. Since all the agents act independently, when then I have to impose the boundary conditions, I have to make sure that the net mass injected in the channel is 0. What people normally do, and actually makes sense, is taking all the actions by all the actors and then you subtract the mean. It's fine, you don't get values that explode or so. The problem is that if you're working, especially if you're working with small values, or values that are centered around 0 with a mean that could possibly be of the same magnitude of the equation, an agent will say, okay, I see this input. I'll make it go through my forward pass, through my forward pass, and I get an output. Then, when the output gets into the CFD environment, it's completely destroyed by the mean subtraction. So what we get is lucky not credit assignment, and the network is not training anything, because it doesn't have a way to actually interact with the environment. It interacts with the environment with a layer that kills everything. And a solution for this is just in the whole network. The solution is adding a differentiable mean subtraction and a component of the loss that and a component of the loss that tries to favor a set of actions that have zero mean. Sorry, lost here. Okay. 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 The second pathology instead has to do with the essence of reinforcement learning, that is it being a Markovian process. With the Markovian process, we just assume that the next action is just related to the previous set of actions, observations, and the state in general. Which, for a turbulent flow, which has several time scales for the dynamics involved, could not be enough. And if you actuate, and by actuate I mean you change the boundary conditions too fast, then you have the Navier-Stokes solver that basically acts like a filter, and you try. It's like you try to act very fast on very slow dynamics, and basically nothing is happening, or something strange and non-physical happens. But at the same time, if you act too slow because you want to tackle the slow time scales through what happens at the wall, and the dynamics of the wall are too fast, you are missing everything. So this is a pathology of the how we extricate. And then, as I said, the other problem is that it is easy to just look at drag reduction, but very often drag reduction is achieved by just injecting a lot of energy. So we do take care of momentum, fine, but we often really don't have a look at the energy that we need to operate this way at the wall. So it's quite common that these policies cheat, and they just try to flip sign to the maximum actuation at every change of the actuation. That's why it's also called bang-bang policy. It injects a lot of energy in the domain, and it creates some structures in the flow that I will show you later that do not correspond to anything physical. This is this could be called remote hacking, and the easy fix would be to just make the reward aware that make the reward aware that there should be other components to avoid this situation. This is also pretty straightforward. For the temporal issue, we just decided to do some more, to have some more thoughts about how to choose the delta t between two actuations. There's some physics behind this. It would be a bit too long, and I'm running late. But if you want to ask me questions about it and why we chose 5 specifically, I can let you know. And to embed memory, we just added a gated recurrent unit, and that ended up helping a lot, even if the training became a bit slower for obvious reason that added parameters and everything else. Okay, now for the results, as I promised. First of all, a very boring table, and then I'll show you the snapshots. But what I wanted to show here is that with our policy that we call Durham for simplicity, we get on a big box a drag reduction value that is close to opposition control, but still not astonishing. But we also get a value of the dissipation, which is the energy that also takes into account the energy the power that you need to operate at the wall, that is comparable to many other techniques, and to a technique like opposition control mainly. And if you use the vanilla deep reinforcement learning, this value for the energy is negative. So this means that if you have a bang-bang policy, you need overall more energy than just not doing anything at the wall to pump the flow. So drag reduction at that point is something that you really don't care about. Now some other numbers, but I don't want to stop here so long. This is the map of the policy. Again, having a recurrent unit and a few other things, we cannot, in this case, find an exact map like we could do before. But this is the conditional mean of the actions, and this is the standard deviation. And you can notice at least, this is something I should comment more, but I don't have, we should comment more. But at least it's a quite complex and rich map, and not something as simple as a separated hyperbolic tangent. These are some snapshots of what's happening on the detection plane. So the observed input once the policy is running. If the top row is the non-actuated case, then you have opposition, and then you have the reinforcement learning. You can notice that both opposition and reinforcement learning try to make these streaks a bit weaker and a bit longer, and they do it in in just slightly different ways, but it is hard to see it here. What I wanted to show, because this is very common, there are many people in this field that show these plots in their papers, is this. With a bank policy, the vanilla DRL, you clearly have two values of the actuations that are vastly preferred compared to the whole space that generate this standing wave. The standing wave that travels into your domain that is not physical, because you can show that if you expand the size of the domain, the wave will take the size of your box. So it's clearly not physical, it's clearly an interaction with the numerical environment. To prove that we are doing something different, we have two ways. This is this is work in progress, and this framework, we would like to see if there is a different transfer of information from the wall to the layer at which we sample the velocity. There is something promising, but I didn't want to make it too heavy, and I wanted to be a bit more comfortable to present something that I haven't worked on for years before. But we are in contact with the people at MIT, and there's potential future work. But what we can have a look at, and this is the last plot that I'll show you, is the joint probability density functions of the velocity variables at the plane that where we detect. So with the non-actuated case, we have a blob here. This is a very common result in fluid dynamics. With opposition control, you try to shift the peak to a different quadrant. And with our policy, we try to shift it instead to a different one. So these two are actually the best indicators from just the physical variables without information theory, that these two policies are doing something different. And we're gonna explain more in the future what we are doing differently. So this is just to wrap up. All these results about how to change, how to make reinforcement learning work without these pathologies are currently under review for nature communications, but you can check the archive paper whenever you want. We also have a study on heat transfer, which is a simpler phenomenon to tackle, and please feel free to have a look at the report to ask any questions.
Thank you, Giorgia. Any questions, Georgie? One thing is that the discovery of the pathologies is really insightful. And do you think that the reinforcement learning community can learn from these physics engineering insights to, as tricks to the reinforcement learning algorithms?
I mean, some tricks are quite easy to implement, but I understand why they weren't used before, because they required a lot of control on the flow solver, checking some statistics, some spectra, or some things that were not making sense. I mean, yes, I hope so, and I believe that there is still a lot of work to do, because, for example, the gated recurrent unit, I must be honest, was embedded because I thought, yeah, okay, that will work. I'm giving memory to the flow, but I didn't tune it that much. I think that there's more work to do, definitely. Also to make it a bit faster, and to allow to have a training directly on the big box rather than a small box and then the inference on the big one.
And in the network design as well, that kind of connections are added to just mimic time stepping, earlier time stepping.
Yeah, somehow, yes.
It's and that usually works well. Maintain the memory.
Yeah.
Any other questions? Computational parts of it, you mentioned slightly about the GPU implementation, but the number of simulations you needed and the type, compute hours you needed for.
Look, I can tell you, these boxes are small, so I train them on one GPU for simplicity on a Spark that we have in our department. If I want to do 200 episodes, it takes 1 day.
100 episodes.
200 episodes? No, okay, sorry, no. About 100 episodes, it takes 1 day.
And each simulation is evolving in time?
Yeah, each simulation is evolving in time, and they simulate a total of 1800 time units in non-dimensionalized time, which is quite standard. Like if you have a look at papers that do this, they always do episodes that are 1500, 1800 time units. So quite common. So what I'm saying is that, especially if you have a small box, this is definitely feasible even without an 800. I had these results in 3 days.
And how do you implement the actions? You just sample a new surface or?
To implement the actions,
Yeah.
you just change the boundary conditions.
Just change
You send the array with the boundary conditions to the CFD solver from Python, and then you recall the routine that defines the boundary conditions to that array. So yeah, minimal edits to recall, like 2-3 lines. 2-3 lines after you communicate.
Yeah. Any other questions? If not, I'll let you also have a train.
Yeah.
Let's thank all of our speakers and the audience for this such a nice session. So thank you for coming.